Your glasses correcting blurry vision, or a telescope pulling a distant galaxy into focus, these are simply the result of light following a few strict geometric rules. The most basic rule is reflection. When light bounces off a surface, the angle it hits exactly matches the angle it leaves. A common mistake is measuring angles from the mirror's surface. Always measure from the perpendicular normal line. If light crosses into a new material, it changes speed. Entering water, it slows and bends toward the normal line. This is refraction. Mastering these straight-line interactions is the required first step. Once you have this geometric foundation, we can start solving for the curved lenses that actually shape our world. When we move to curved mirrors, we use the mirror formula to find image distances. And this is exactly where students panic, plugging in numbers and freezing up when a result is negative. This XY coordinate graph shows the new Cartesian sign convention. By treating the mirror's pole as the origin, you can map the math directly to physical space. The rule is simple. Trace the direction the incident light is traveling. Distances measured in that direction are positive. Anything measured in the opposite direction is negative. So an object sitting in front of the mirror will always map into negative territory. Pause here and test yourself. If you place an object exactly at the center of curvature, where do the reflected rays intersect? They converge right back at that exact same point, creating an inverted image of the exact same size. This geometry has physical weight. Look at this concave solar cooker. Its specific physical curve is engineered to force incoming parallel sunlight to intersect perfectly at its focal point to heat the pan. Internalizing that coordinate plane is your safety net. If you know how the physical geometry behaves, you will instinctively know whether your mathematical answer should be positive or negative. When calculating for thin lenses instead of mirrors, the equation changes. The lens formula is identical to the mirror formula, except for a single minus sign. Do not mix these up. Refraction also creates a specific phenomenon called total internal reflection. This exact mechanism is the reason high-speed fiber optic internet exists. For this to happen, two strict conditions must be met. Light must travel from a denser medium into a rarer one, and the angle of incidence must be wider than the material's critical angle. Once past that threshold, the light stops exiting the material and reflects entirely inside. Looking at these exposed fiber optic strands, you are seeing that math in action. By designing the glass core to guarantee the light hits the boundary past that critical angle, the data pulses are permanently trapped inside the cable. Applying these precise edge case rules of refraction allows us to bounce light across thousands of miles of ocean without losing a single bit of data. How do these individual rules operate when we stack multiple lenses together to build an instrument? In a compound microscope, the magnification process compounds in steps. The first lens, the objective, creates a real image of the specimen. Then the second lens slides in, uses that initial image as its object, and magnifies it vastly larger. You can see that two-step process in the hardware of a laboratory microscope. The spatial gap between the objective lens near the slide and the eyepiece at the top provides the exact focal distance needed for that compounded magnification. Telescopes reverse this priority. Instead of magnifying tiny objects, they must capture extremely faint parallel light rays from infinity. That is why instruments like the Hubble Space Telescope are built with massive objective apertures to collect as much light as possible. Remember the core rules. Mirrors use a plus sign, lenses use a minus sign, and the direction of incoming light sets your positive axis. Practice sketching those 6 primary diagram shapes daily, and you will have this chapter locked down.